Hi everybody, this is Math 025, part 3 for Module 1, and here we're going to look at perfect square trinomials today, factoring hard trinomials, and then also difference of perfect squares and sum or difference of cubes. So this one will be a pretty packed video. The first thing we're going to talk about are going to be perfect square trinomials. Now they are going to, you could factor them the same as we did in Module 1, Part 2, where we did the easy trinomials. But sometimes perfect square trinomials, the values for A and B could be larger numbers. So if you recognize that it's a perfect square trinomial, it's just a little bit easier to factor. It goes a little bit quicker. But again, you can factor it the same way we did before. What a perfect square trinomial is if you look at your trinomial that you're given and you notice that the first term is a perfect square and that last term, the third term, is a perfect square. If you notice those are both perfect squares, then you want to check that middle term and you want to check the signs on your trinomial. So if the middle term is, if you can take the square roots of your a squared and your b squared, multiply them together and times it by 2, so 2ab, and that's the middle term, then this is more than likely a perfect square trinomial. One thing you do have to watch, you have to watch your signs. If you have two plus signs, or a minus and a plus in that order, then when you factor your perfect square trinomial, it is going to factor for the two plus signs. It would be a plus b, the quantity of a plus b squared. And if you have a minus and then a plus, it's going to factor into the quantity of a minus b squared. And a and b would just be the square roots of your first and your last terms. And so you can kind of see on here, they showed the previous method that we did where we multiplied, found the numbers that multiply to 16 and then add to -8. And then we checked to see if it was a perfect square trinomial, and it is. Again, just recognizing those perfect square trinomials, it just helps you factor a little bit quicker. It's a little bit more efficient, especially if you have a large b value. But if you don't remember that and you factor it the old way, that's okay too. But again, we're going to look at some and just practice factoring them as perfect square trinomials. All right, so here for A, we have x squared plus 14x plus 49. And one thing that I recognize right away is I know 49 is a perfect square. I know the square root of 49 is 7. And then I also know the square root of x squared is x. So here, I had to get A, I did the square root of x squared, and that equaled x, and that's my A. And the B was the square root of 49, which was 7. So now I need to look at 2A, and, finding 2AB. So if I take and I multiply A times B, or x times 7 times 2, that will give me 14x, which does give me that middle term. So I do know that I can factor this as a perfect square trinomial. So when I factor it, it is going to factor. Remember, to get 49, we multiply 7 times 7. So initially, it's going to be x plus 7 times x plus 7. But we always want to write things as simplest form. And here we have two of the same factors. So instead of writing it this way, the simplified version would be x plus 7 to that second power. Again, you want to simplify as much as can, and because the two binomials are the same, we write it with the squared on it instead of leaving it in the two binomials. All right, now for B, I have a minus and then a plus. So it could be a perfect square trinomial. I do know the square root of p squared is p, so that's nice and easy. And then I do know that the square root of 144 is also 12. So I check that middle term, and if I multiply p times 12, I get 12p, and then if I times it by 2, it is going to give me 24. So when I factor this one, it will be factored as p minus 12 times p minus 12, or again, we're going to simplify it and make it p minus 12 squared. Now for C and D, if you look at those, you're like, oh, they don't look like perfect square trinomials because we got a 3 there. But again, always look for that greatest common factor. And I do recognize here that I can factor out a 3 from C. So when I do that, I'm going to have 3 times B squared plus 8B plus 16. And now my trinomial here, 16 is a perfect square, B is a perfect square. The square root of 16 is 4. The square root of B squared is B. B times 4 is 4B, but if you multiply it by 2, you get 8B. So my final factoring here, because it's 2 plus signs, would be 3 times B plus 4 squared. Let's see, for D here, I definitely can pull out a 2, and also all three have y's, so I'm going to pull out 2y to the second. So then I'll put my 2y to the second on the outside. That's going to leave me with y squared minus 12y plus 36. And then y squared and 36 are perfect squares. The square root of 36 is 6. The square root of y is y. So 6y times 2 would give me 12y. It is a perfect square trinomial. So we're going to factor this as 2y squared times y. And because that first sign is a minus, it's going to be minus 6 squared. So my final factoring there is 2y squared times the quantity of y minus 6 squared. So now we're going to look at factoring trinomials in the form of ax squared plus bx plus c. So here we're going to have a coefficient other than 1 in front of the x squared. These are often referred to as hard trinomials since it takes more steps to factor than the easy trinomials. Now, there's different ways to factor these. When I was in school many years ago, I'm kind of old, but they did factoring by trial and error. So you just had to look at the combinations of factors and mess around them. And it worked, but it was a little cumbersome at times. I did find a method that I feel like helps students factor pretty easily, and that's factoring by the box method. So that's what I'm going to teach. But if you have another method and you like to use it, you can. You can factor hard trinomials using the grouping method. You can factor them. There's other methods out there. I know some people call like slide and glide or the diamond method. Whatever helps you factor, you can use. I just pick one method to teach because I feel like if I did multiple methods in the past, it's been confusing for students, and then they struggle with, am I doing the right steps for the method that I'm using, and they get them confused. So again, I only teach one method to show the factoring, but I encourage you, if you know another way and you're getting the right answers, it's okay to use that method. Just show your work so we can see your steps. So now, when you factor a hard trinomial, the first thing you always want to do, again, look for that GCF, if there's one to pull out. And then you're going to find two numbers that multiply to get the product of a times c. So here, we're not looking at the factors of just c. We're looking at the factors of a times c. And then are going to add to give us that middle coefficient of b. And then once we find those, we're going to factor it using the box method. And I'm going to show you how to do that when we look at some on the next few slides. All right, so here we have for a, 3x squared plus 10x plus 8. And when I look at this, there is no greatest common factor to factor out. So now I need to factor it, see if it's factorable. So I am going to draw my box. And you simply just draw a box. My drawing skills are not great, and then on a computer they're even worse, but a box with four squares in it. Your first term, the 3x squared, always goes in that box, the first box, and then the 8, and it doesn't matter the sign of the 8, the last term always goes in the last box here. And the other two boxes are reserved for the middle terms, and I often forget to put my variable there, so whatever your variable is on your middle term, go ahead and put that in and put a line. We're going to put some numbers in there. But to get these two numbers, we need to do our AC method. So we're going to multiply A times C, or in our case, 3 times 8. We know that equals 24. So now we're going to look at our factors of 24. I know I have 1 and 24, 2 and 12, 3 and 8, and then 4 and 6. Now, I need to find two factors. I have two plus signs, so they're both going to be positive numbers that will also add to give me a 10. So I know 1 and 24 isn't going to work. 2 and 12 will not add to give me 10. And I need two plus signs, so it's not going to work. 3 and 8 don't work, but 4 and 6 work. So those are going to be the two terms that I am going to use when I do my factoring. So I'm going to put, and it doesn't matter where I put the 4, where I put the 6. I'm just going to put the 4 here and the 6 here, but if you switched it, that's okay. And then I'm going to take the sign for the 4. Because I know I have two plus signs here, I know these are both positive numbers. So that 4, I'm going to put that plus sign up there. And that 6 I know is going to be positive, so I'm going to put the plus sign out there. And that is the only signs you need to worry about when you're doing your factoring by box method. I don't put any signs in the box. Sometimes you'll see people that do. I don't feel it's necessary. And now what we are going to do is we are going to factor our box. So we're going to find the GCF. And so we are going to first, it doesn't matter if you go across or up first, but I'm going to go across first. For the bottom two boxes, I'm going to find the greatest common factor for 6x and 8. So for 6x and 8, my greatest common factor is going to be a 2. And then I'm going to go across. On the top, we have 3x squared and 4x. Now, for 3 and 4, the GCF is 1. But then we have x squared and x. So remember, choose your lowest power. So we're going to have an x there. So that binomial is x plus 2. Now what I'm going to do is I have to factor up. So I'm going to factor these two boxes. I'm going to do 3x squared and 6x. My GCF for 3 and 6 would be 3. And then again, I have x squared and x. So I'm going to put my x there. And then we're going to factor up these two. 4x and 8, my GCF would be a 4. So now we are done factoring. My factored form of 3x squared plus 10x plus 8 is going to be 3x plus 4 times x plus 2. Because these become our two binomials. All right, let's try it with B. And, if you want, pause the video, try it, see what you can do. Again, we need our box. So here's my box, my 4 corners inside the box. In that first upper left-hand corner, we're going to put our 2p squared. In the bottom right-hand corner, we're going to put our 18. And again, I have two plus signs, so I know both my factors are going to be positive. Don't forget your middle variable, that p goes in those other two boxes, the upper right and the lower left. And what we are going to do now is we're going to multiply a times c. So a times c is 2 times 18, and 2 times 18 is 36. So we're going to put our 36 there. And now find our factors of 36. We have 1 and 36. 2 and 18, 3 and 12, 4 and 9, and then 6 times 6. Now, we have two plus signs, so I know both factors are going to be positive, and I need something that's going to add to 13. So if I look at my pairs, 1 and 36 won't work, 2 and 18 don't work, 3 and 12 equals 15, close, but doesn't work. 4 and 9, that will add to 13, and we know 6 plus 6 is 12, so that doesn't work. So I'm going to use 4 and 9. Again, doesn't matter where I put them. I'll put the 9 there this time and the 4 here. Both are positive, so I'm going to put two plus signs out there, on the top row and then the left-hand side of the box. And now I'm going to factor. So again, I'm going to factor across. 4p and 18, my greatest common factor there is going to be 2. When I look at 2p squared and 9p, my greatest common factor there is just going to be p, because 2 and 9, the GCF is 1. Now I'm going to factor up. So 2p squared and 4p, the GCF would be 2p. And then 9p and 18, my GCF will be 9. So my factored form here is p plus 2 times 2p plus 9. And again, if you want to check it, FOIL it to make sure it's correct. I encourage you guys to do that if you need to. All right, let's take a look at C. First thing, again, look for that GCF. I don't see a greatest common factor for 4b squared, 3b, and 7. So I'm going to go ahead and draw my box. All right. And then again, put my 4b squared in the upper left-hand corner, my 7 in the lower right-hand corner, and again, it doesn't matter the signs. And then because my middle variable is a b in the upper right and the lower left box, I'm going to put a b and the line so I can put my numbers in there. Now, we're going to multiply a times c. So 4 times 7 is 28. So if I look at my factors of 28, I know I have 1 and 28, 2 and 14, and 4 and 7. Now I have two negative signs. So if you recall from before when we were factoring, when we have two negative signs, actually what we're going to need when we multiply is going to be one positive and one negative. Because remember, to get that negative last term, I have to have a positive and a negative number. So I need to look through and see if I can find a combination where I can use one positive and one negative that will add to give me negative 3. I know I can't do it with 1 and 28 or 2 and 14, but 4 and 7 I can do that. I need a negative 3, so that means my 7 needs to be negative and my 4 needs to be positive. So now I'm going to put those numbers in my chart, and again, it doesn't matter where I put them. I'll put the 4 in the upper right-hand corner, so that means the plus sign, because the 4 is the positive, will go on that top of the box. I'm going to put the 7 in the lower left corner, and because that was negative, that negative sign will go outside the left-hand side there. And now I don't have to worry about signs anymore, so I think it's nice and easy when you put those signs in right away. Okay, now let's factor across. For 7b and 7, my GCF is 7. For 4b squared and 4b, my GCF will be 4b. And then when we factor up, 4b squared and 7b will be a b for my GCF. And then 4b and 7, my greatest common factor here is just a 1. And we do want to put that 1 in because we need it. So now my factored form is going to be 4b minus 7 times b plus 1. And it doesn't matter the order that you write those two binomials. Just you need to put them down there because it's commutative, it's multiplication. All right, let's look at D. When I first look at this, I say, oh, there might be a GCF because I have 5 and 10. But 5, none of the factors for 5, which are just 1 and 5, go into 27, so it won't work. So let's do the box method. I'm going to draw my box. Okay, and in the upper left-hand corner, we'll put our 5y squared. My lower right hand will be my 10. Here we have a minus and a plus. So I know my two signs are going to be negative. I'm going to put my y's right there. And now let's do our a times c. So 5 times 10 is 50. When I look at my factors of 50, I have 1 and 50, 2 and 25, 5 and 10, and I think that's it. So now I need I need a positive 10, which means I either have to multiply two positive numbers together or two negative numbers, and I need a negative 27. So it's going to be two negative numbers. And I need those two negative numbers to add to negative 27. So 1 and 50 won't work, and 5 and 10 won't. But 2 and 25 will. So I'm going to put my 2 here, and I know it's a negative 2. So I'll put a negative on the top of the box. And it's a negative 25, so I'll put my 25 there and put my negative on that left-hand side. And now I just need to factor out the greatest common factor. So again, we'll go across the bottom first. 25y and 10, my GCF would be 5. For 5y squared and 2y, my greatest common factor would be y. When I factor up, for 5y squared and 25y, my greatest common factor would be 5y. For 2y and 10, my greatest common factor will be 2. So our final factored form is y minus 5 times 5y minus 2. All right, so now we're going to look at our last two here to factor. And when I look at E, I do definitely see a hard trinomial there. I see 4q squared plus 20q plus 25. But I do notice that 4q squared is a perfect square and 25 is a perfect square. So I'm thinking here I might have a perfect square trinomial. I could factor it doing the box method, but first I want to check it out to see, can I just factor it a little bit easier? First, I'm going to look at the square root of 4q squared, and I know that's 2q, and the square root of 25 is 5. So now if I look at 2ab, if I multiply 2 times 2q times 5, that's going to give me 20q, which is that middle term. So I have a perfect square trinomial here with two plus signs, so I don't need to do the box method here. I can just factor it. Remember, if it's a perfect square trinomial with two plus signs, it factors to a plus b squared. So I'm going to factor this. My a is 2q. My b is 5. So I have 2q plus 5 squared. Take a look at f. 16t squared, perfect square. 9, perfect square. We have a minus and then a plus. So remember, if it's a minus and then a plus with your perfect squares, it factors to a minus b squared. Let's double check to make sure that middle term works. 16t squared, the square root of that is 4t. The square root of 9 is 3. So if I do 2ab, that would be 2 times 4t times 3. 4 times 2 is 8, times 3 is 24. We have 24t there. So it works. So when I factor this, I'm just going to have 4t minus 3 squared. So again, notice how easy and quick that was because I recognize those perfect square trinomials. So that is a good thing to look for. Now, if we'd done E with the box method, we'd done 4 times 25, which is 100. It's not a huge number, but it will take a little bit of work to find all those factors and see which ones would add to give us 20. So we saved ourselves a little time by recognizing those perfect square trinomials. All right, so far with factoring, we've looked at pulling out our GCF, which we should do automatically no matter how many terms we have. Then we started looking at different types of factoring. We found if we had 4 terms, we factored by grouping. If we had 3 terms, it was either an easy or a hard trinomial, and we factored it into 2 binomials. Now we're going to look at factoring of different squares. So this is another one where it's really easy, but it looks hard because we often forget about it. But your difference of squares, okay, difference means subtraction. So anytime we're factoring here, you have to have a binomial that has subtraction, and both the first and the second term need to be perfect squares. So if you have two perfect squares. So you have two terms, they're both perfect squares. It will always factor into a plus b times a minus b. So you take the square root of a squared and b squared, and then you put it into factoring. So if we take a look, you can see the example they did here. We're going to look down here. We have x squared minus 9. I have two terms here. I have subtraction. X squared is a perfect square and 9 is a perfect square. The square root of x squared is x. So here I'm just going to write out my a will be x. My b, the square root of 9 is 3. So when I go to factor it, it's going to factor into x plus 3 times x minus 3. And that's all you have to do there. For b, again, I see some perfect squares there. I know the square root of 4 is 2. The square root of p to the 4th is p squared. The square root of 49 is 7, and the square root of q squared is q. So if I look, like this is my a and this is my b. So a, in this case, or this is my a squared and my b squared, the square root of a squared is, again, 2p to the 4th, because we took the square root of this. And then b is going to be 7q. So when I go to factor it, again, it's going to have both a and b with the plus sign and a and b with the minus sign. So it's going to be 2p to the 4th plus 7q. And it doesn't matter if you put the plus or the minus first. And then 2p to the 4th minus 7q. All right, let's take a look here at C. Again, I have two terms, but I'm noticing they're not perfect squares. However, again, always check, is there a greatest common factor you can pull out? Yes, in this case, we can pull out a 7, so I can factor out a 7. So we're going to have 7 times b squared minus 1. Now, if I look at that inside term, b squared and 1, which we don't often think of, they're both perfect squares, so we can factor it. And my final factored form is going to be 7 times the square root of b squared is b. The square root of 1 is 1. So b plus 1, b minus 1. And that's our final factored form there. For D, again, I do have a greatest common factor I can pull out here. I can pull out, let's see, for 20 and 45, I can pull out a 5. And I have y to the 5th and y cubed, so I can pull out a y cubed. So when I factor that out, I'm going to end up with 4y squared minus 9. Again, two terms, subtraction, they're both perfect squares. So my final factoring will be 5y cubed times the square root of 4y squared will be 2y plus the square root of 9 is 3. And then we just need to have 2y minus 3. And that's my final factored form. Now for E, I do not have any greatest common factor to factor out. But I know the square root of q to the 4th power is q squared, and the square root of 81 is 9. So when I factor this, I have q squared plus 9, and then q squared minus 9. And if I look at this, I'm saying, okay, I'm done here. But be careful, because you always want to make sure everything is factored completely. Q squared plus 9, I have addition here. I can't do anything with it. But here I have q squared minus 9. Q squared and 9 are both perfect squares, and there's subtraction there. So this term right here, or this factor, I can factor it again. So my final factored form here is I'm going to keep my q squared plus 9. I can't do anything with it. But q squared minus 9 can be factored into q plus 3 times q minus 3, because the square root of q squared is q and the square root of 9 is 3. So you got to watch for those. They will try to give those to you. You will see them on tests and quizzes quite frequently. And it works with 81 because the square root of 81 is 9. It's just perfect square. And then also 16 because your square root of 16 is 4. So kind of look for, if you have something to the fourth power, an 81 or 16, you're going to have to factor it twice. Let's take a look at F, our last one here. I do need to pull out a GCF. I'm going to pull out 2t to the third power. So that is going to give me t to the fourth power. I'll keep my 2t to the third here. I'll draw a little line. Minus 16. Look at that. I was just talking about this, so now I can factor this again. So we have 2t to the third power. I can factor this. It's difference of perfect squares. It's going to become t squared plus 4 and t squared minus 4, which if you look, the t squared plus 4, it's addition. I can't do anything with it. It's not factorable right now. But t squared minus 4 is, I can do difference of perfect squares again. So I'm going to have 2t cubed times t squared plus 4. And then it's going to be t plus 2 times t minus 2, because the square root of t squared is t, the square root of 4 is 2. So you do want to be on the lookout for those. Make sure you factor everything completely. So once you do the factoring, can you factor again? Okay, so here, we are going to use our difference of perfect squares, but you're probably saying, well, this is weird because it doesn't have 2 terms. G has 4 terms. You're right. But what we're going to do here is, remember, we don't have a greatest common factor to factor out here, but I have 4 terms. So 4 terms we factor by, hopefully you're saying grouping. So again, I'm going to group these. I'm going to start by factoring by grouping. So for the first pair, I can factor out an x squared. So I'll have x squared, and it will be x plus 1 when I factor out an x squared from both of these terms. Now, remember, the second pair, the leading coefficient in that pair is a negative. It's a negative 1. So I'm going to factor out a negative coefficient. So I'm going to factor out here a negative 1 because my GCF is 1. I'm going to factor out a negative GCF. And so when I divide by negative 1 here, negative x divided by negative 1 gives us a positive x. Negative 1 divided by negative 1 gives us a positive 1. Which then is nice because it allows us, we got that common factor of x plus 1. So we're going to factor that out. And that's going to leave me with x plus 1 times, I'm going to have x squared minus 1. And when I look at this, I have x plus 1 times x squared minus 1. X plus 1, factored prime numbers, I can't do anything with it. But here, x squared minus 1, both perfect squares and subtraction. I can factor it again. So my final answer, or when I start off, I'm going to have x plus 1 times x plus 1 times x minus 1, because x squared, the square root is x, and 1, the square root is 1. Now, I can do one more thing to simplify this. I do have 2 x plus 1s here. So remember, you want to write it in simplest form. We want to write it as a power. So we'll do x plus 1 squared times x minus 1. And that's our final answer there. Now, for h, we have an easy trinomial here. So let's go ahead and see if we can factor it. When I look at it, I am going to, let's see, the factors of 4 are 1 and 4 and 2 and 2. I have a minus and a plus, so I know I'm going to have 2 negatives, and they have to add to 5. So I'm going to use negative 1 and negative 4. So when I factor it, I'm going to have a squared minus 1 and a squared minus 4. Ooh, when I look at that, bells should go off. I have 2 terms right here, subtraction, and they're both perfect squares. And the same thing here, 2 terms, subtraction, both perfect squares. So I can factor both of these again. My a squared minus 1 is going to become a plus 1 times a minus 1. And then my a squared minus 4 becomes a plus 2 times a minus 2. And then we don't have any like factors here to combine into a power. So this is our final answer. But it took it from an easy trinomial where we should have 2 binomials, and we turned it into having those 4 binomials there. So again, you just have to look at your problem, make sure it's factored completely. All right, the last type of factoring that we are going to look at for Module 1 here is going to be factoring a sum or difference of cubes. Sometimes when you have 2 terms, they're not going to be perfect squares, and it may not always be just subtraction. So here, for difference or sum of perfect cubes, you can have addition or subtraction. So if you have 2 terms and they're not perfect squares, the next thing you want to check to see if you can factor anything, if there's no GCF you can pull out, is to look, are the 2 terms perfect cubes? And if they are, we can factor perfect cubes. If it's the sum, and I know this is kind of small here, I don't know why, but I'm sorry. If you have the sum of perfect cubes, so you have 2 terms, they're both perfect cubes, you would factor that into a plus b. So you're going to take the cubed root of a cubed and b cubed. So you're going to do the quantity of a plus b times the quantity of a squared minus ab plus b squared. If it is subtraction, so difference of perfect cubes, it's going to be the quantity of a minus b times a squared plus ab plus b squared. And this is one formula, I would encourage you guys to practice quite a bit, know it, memorize it, so it's easy, it's natural to help you factor it quickly. And you can take a look at the example they did here and review it. And we're going to practice on the next page. All right, so we're going to take a look here. And for A, I look at this right away, and I see 2 terms in subtraction, so I'm going to think difference of perfect squares. But I also know x cubed is not a perfect square. 64 is, but I can't factor out a GCF, so I can't do difference of perfect squares. But I also know that 64 is a perfect cube. I know that the cubed root of x cubed is equal to x, and then the cubed root of 64 is equal to 4. So I can use my difference of perfect cubes to factor here. And remember, that formula is going to be a minus b times a squared plus a times b plus b squared. So I'm going to go ahead and fill in my values. I'm going to have x minus 4 times a is x, so a squared would be x squared, plus multiply x and 4 together, you get 4x, plus 4 squared will give me 16. And that would be our difference of perfect cubes. For B, if I look at that, I can see that there is, again, no GCF I can factor out, and they aren't perfect squares, or at least the 125 and q cubed is not. But I can take the cubed root of p to the 6th power. Remember, 3 goes into 6 twice, so it would be p squared. And the cubed root of 125q to the 3rd power is going to be 5q. So now I'm going to factor using my sum of perfect cubes, which is going to be a plus b times a squared minus ab plus b squared. And here's the thing to remember. These formulas are exactly the same except for the signs. If it's a subtraction, your subtraction sign goes first, and then you have all plus signs. If it's addition, your addition sign goes first, and then the subtraction, and then the addition. So you always have 2 plus signs and 1 minus sign. Just the order changes depending on if it's the sum of perfect cubes or the difference of perfect cubes. So I'm going to go ahead and fill in my values. I'm going to have p squared plus 5q times, if I square p squared is going to give me p to the 4th power, because you add those exponents, minus 5p squared q, because I'll multiply the two together, plus 25q squared, and I got that because I took 5q and I squared it. And that is my final answer there. All right, so here when we look at C, I see two terms and I see subtraction, but I don't see perfect squares, and I don't see perfect cubes right now. But is there a GCF? We can factor out here a 3. So I'm going to factor out a 3 from both terms. And it's going to leave me with b cubed minus 8. And I'm going to keep my 3 out there. Now, I do know the b cubed minus 8. 8 is the cubed root, or the cubed root of 8 is 2. And the cubed root of b cubed is b. So I can refactor this as my difference of perfect cubes. And I can have it as 3. The cubed root of b cubed is b. The cubed root of 8 is 2. And then we need that first term squared, so it's going to be b squared plus, multiply the two together, so 2b, plus square that last term of 4. So there's my final answer there. For D, let's see here. I definitely don't see any perfect cubes yet, but I do see a greatest common factor. I can factor out a 5y squared here. So when I do that, I'll keep that on the outside, and that's going to leave me with 1,000 y cubed plus z cubed. Because the 5 and the y squared equal 1. Now, I do have perfect cubes here. So the cubed root, I'll just write it up here so you can see it. The cubed root of 1,000 y cubed is 10y. And the cubed root of z cubed is z. So this is the sum of perfect cubes. So I'm going to keep my 5y squared. And then I will have 10y plus z, as you do a plus b. And then we're going to take that first term, 10y squared, so we get 100y squared, minus, multiply the two together, so 10yz, plus square the last term, so you get z squared. And that will be our final answer. It's a little bit long, but it is in final factored form. All right, here we're going to look at our last two problems that we're going to factor for this module. Again, this first one, we have 4 terms here with no greatest common factor for all 4. And remember, when you see 4 terms, again, I want you to think, we're going to factor this by grouping. So we are going to group them together, the first 2 and the second 2 terms. My greatest common factor here will be x cubed, so I'm going to factor out an x cubed for the first 2 terms. And that will give me x cubed times x plus 1. And then I'm going to factor out a 27 here. So I'm going to have x plus 1 there, which now, again, I can factor this by grouping because I have x plus 1 as my greatest common factor in each term. So it's going to end up being x plus 1 times, for the first term, x cubed will be left. For the second one, the 27 plus 27. So now it looks like it's done, but I do need to look. X plus 1, it's a product of primes. I can't factor it anymore. But x cubed plus 27, that's my sum of perfect cubes. They're both perfect cubes. The cubed root of 27 is 3, and the cubed root of x cubed is x. So now I got to factor it. I'm going to have x plus 1, and then I'm going to do a plus b, so it's going to be x plus 3 times, we're going to square that first term, so x squared minus 3 times x is 3x plus 9, because you square the 3. So this will be our final answer. You do want to check that trinomial and see if we can factor it. But x squared minus 3x plus 9 cannot be factored. So if it could, we would factor again. But this is our final answer here. And then when we look at f, first I see subtraction in 2 terms. So I am going to check for difference of perfect squares. And I know that 64 is a perfect square, and t to the 6th power is also a perfect square. So I can go ahead and factor this as, if I do my difference of perfect squares, it's going to become the square root of t to the 6th power is going to be t to the 3rd power. And the square root of 64 is 8. So I'm going to have t cubed plus 8 times t cubed minus 8. Oh boy, that's going to make for some busy times here, because I can factor this. T cubed plus 8 and t cubed minus 8. That's the sum of perfect cubes and the difference of perfect cubes. So I'm going to factor this one first. Let's do that. The t cubed plus 8, because the cubed root of 8 is 2. So that is going to become, I need a lot of space. I'm going to move down here. T, and I think I'm going to need more space than that. Let me move it over. All right. So we're going to have t plus 2 times t squared minus 2t, because again, you square that first term, multiply a and b together, and then plus 4. And then I have to factor t cubed minus 8, so that's going to be t minus 2 times t squared plus 2t plus 4. And that will be our final answer. I don't believe... actually, we might be able to... No, we won't be able to. I was looking at the trinomials to see if we had any factoring that we could do here, but we can't. They're not factorable any further. So that is our final answer there.